All your life you have believed that our solar system works in simple, predictable ways. But what if I told you that some of the facts you grew up with were never true to begin with? Not mistakes, myths that survived because nobody ever questioned them. Most people don't realize the sun isn't a still, glowing ball, but a twisting giant that spins like a cosmic storm. Or that the moon's phases have nothing to do with Earth's shadow. That is an illusion we were all taught to believe. And the moon itself? It does rotate, just perfectly locked in a way that hides its real dance. We were told the moon affects human behavior, that crossing the asteroid belt is a deadly gauntlet, and that Saturn alone wears rings. But the truth is far stranger. Uranus has thin, dark rings you can barely see, and Neptune hides rings so faint they were almost lost to time. Do not forget to leave a like and subscribe to the channel, as tonight we uncover 7 lies you were told about the solar system, and the real story is far more mysterious than the myths. Let us begin. Today, we are going to examine 7 of the biggest lies you have been told about our solar system. These are not minor details or obscure technicalities, but fundamental misunderstandings about major solar system objects and phenomena. Some of these myths have been taught in schools for decades. Others persist in science fiction and popular media, despite being thoroughly debunked by scientific research. Each one reveals something important about how our solar system actually works, and shows how easy it is for even well-educated people to carry around false beliefs about the universe. Chapter 1. The Sun does not rotate on its axis. When you think about the Sun, you probably imagine it as the stable, unchanging center of our solar system, a fixed point around which everything else revolves. This mental image is reinforced by diagrams in textbooks showing the planets orbiting in neat circles around a stationary yellow ball. The Sun sits there motionless while Earth, Mars, Jupiter, and the other planets dance around it in their eternal cosmic ballet. This picture is so common and so simple that most people never question whether the Sun itself might be moving or rotating. The truth is that the Sun does rotate on its axis, just like Earth and the other planets. This rotation was first observed in the early 17th century when astronomers began tracking sunspots, dark patches that appear on the Sun's surface. By watching how sunspots moved across the face of the Sun over time, astronomers could determine that the entire Sun was turning. What they discovered was far stranger than simple rotation. The Sun does not rotate as a solid body the way Earth does. Instead, different parts of the Sun rotate at different speeds, a phenomenon called differential rotation. At the Sun's equator, one complete rotation takes approximately 25 days. This means that if you marked a specific point on the solar equator and watched it, that point would return to the same position after about 25 days. But if you move toward the Sun's poles, the rotation period becomes longer. At mid-latitudes around 40 degrees from the equator, the rotation takes around 27 to 28 days. At the poles themselves, one complete rotation requires about 34 to 36 days. This means the Sun's equator is racing ahead of the polar regions, with different latitudes sliding past each other at different speeds. How is this possible? The answer lies in the Sun's composition. Unlike Earth, which is a solid rocky planet that rotates as a single rigid body, the Sun is made entirely of plasma, a state of matter where atoms are broken apart into electrically charged particles. Plasma behaves more like a fluid than a solid, allowing different parts to move at different rates. The Sun's differential rotation is driven by complex convection currents deep inside the star, where hot plasma rises from the interior, cools at the surface, and sinks back down in an endless cycle. This differential rotation has profound effects on the Sun's behavior. The varying rotation rates create shear forces that twist and tangle the Sun's magnetic field lines. These tangled magnetic fields give rise to sunspots, solar flares, coronal mass ejections, and other forms of solar activity that can affect Earth's magnetic field and atmosphere. Understanding solar rotation is crucial for predicting space weather and protecting satellites, power grids, and communication systems from solar storms. The relationship between differential rotation and solar activity is complex and fascinating. Research shows that the Sun rotates more differentially during the rising phases of sunspot cycles than during the falling phases. This means that when solar activity is increasing toward a maximum, the difference in rotation speed between the equator and the poles becomes more pronounced. Conversely, when solar activity is declining toward a minimum, the differential rotation decreases and the Sun rotates more uniformly. The magnetic field plays a central role in this behavior. Strong magnetic fields appear to affect the rotation rate, with regions of intense magnetism rotating at slightly different speeds than regions with weaker fields. This creates a feedback loop where differential rotation generates and twists magnetic fields, which in turn influence the rotation pattern. This process is known as the solar dynamo, and it drives the 11-year cycle of solar activity that astronomers have observed for centuries. The solar dynamo works through a process called the alpha-omega mechanism. Differential rotation stretches out magnetic field lines in the east-west direction, a process called the omega effect. Meanwhile, rising and sinking convective flows twist these stretched field lines, creating new north-south components in a process called the alpha effect. Together, these two effects amplify and regenerate the Sun's magnetic field, creating the cyclical pattern of solar activity we observe. Every 11 years, the Sun's magnetic field flips, with the north and south magnetic poles reversing positions. Recent studies using helioseismology, a technique that analyzes waves traveling through the Sun's interior, have revealed additional layers of complexity. Scientists discovered long-period oscillations at high solar latitudes that appear to modulate the differential rotation pattern. These oscillations may provide a regulatory mechanism that prevents the polar regions from slowing down too much relative to the equator. The oscillations have periods of several years and show correlations with solar activity cycles. The discovery that the Sun rotates at different speeds at different latitudes was revolutionary when first confirmed in the 17th century. The astronomer Christoph Scheiner reported in 1630 that observations of sunspots revealed different rotation periods at different latitudes. His measurements were remarkably accurate and agree well with modern values. This discovery challenged the prevailing view that celestial bodies were perfect, unchanging spheres, and demonstrated that the Sun was a dynamic, evolving object. Galileo Galilei also observed sunspots and tracked their motion across the solar disk in the early 17th century, though he was initially cautious about interpreting what the motion meant. The observation of sunspots was itself controversial at the time because it contradicted the Aristotelian doctrine that the heavens were perfect and unchanging. Dark blemishes on the Sun suggested imperfection, and the fact that these blemishes moved suggested change and activity. The Catholic Church, which held considerable influence over scientific discourse in Europe, was not pleased with observations that contradicted established doctrine. Modern observations of the Sun's rotation use much more sophisticated techniques than simply watching sunspots drift across the solar disk. Astronomers now use spectroscopy to measure the Doppler shift of light from different parts of the Sun, determining how fast each region is moving toward or away from us. When a source of light moves toward an observer, the light waves are compressed and shifted toward shorter, bluer wavelengths. When the source moves away, the waves are stretched and shifted toward longer, redder wavelengths. By measuring these shifts precisely, astronomers can determine rotation speeds at different latitudes with great accuracy. They also track magnetic features in the Sun's chromosphere and corona using specialized telescopes sensitive to specific wavelengths of light. The chromosphere is the layer of the Sun's atmosphere just above the visible surface, while the corona is the extremely hot outer atmosphere that extends millions of kilometers into space. Both regions contain magnetic structures that rotate with the Sun, and by tracking these structures over time, scientists can map the rotation pattern throughout different layers of the solar atmosphere. Decades of data from ground-based observatories and space telescopes have allowed astronomers to map how rotation rates vary, not just with latitude, but also with time and depth within the Sun. Data from the Kodaikanal Solar Observatory in India, which has been observing the Sun for more than a century, provided valuable long-term records that revealed subtle changes in differential rotation over multiple solar cycles. Space missions like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory have provided continuous high-resolution observations that captured details impossible to see from the ground. The Sun's equatorial rotation speed is approximately 2 kilometers per second. This might not sound particularly fast compared to the speeds we experience on Earth, but remember that the Sun has a diameter of about 1.4 million kilometers. A point on the solar equator travels an enormous distance during each rotation, roughly 4.4 million kilometers in 25 days. The energy involved in rotating such a massive object is staggering, and the differential rotation represents a continuous transfer of angular momentum and energy through the Sun's interior. Understanding solar rotation also helps astronomers study other stars. Many stars show similar differential rotation patterns, and by studying our Sun in detail, we can better interpret observations of distant stars where we cannot directly measure rotation at different latitudes. Rapidly rotating stars tend to show more pronounced differential rotation and higher levels of magnetic activity, including powerful stellar flares much more energetic than anything our Sun produces. Slowly rotating stars tend to have weaker differential rotation and less activity, though there are exceptions to this general pattern. The Sun serves as a laboratory for stellar physics, allowing us to test theories about how stars generate magnetic fields, how they transport energy from their cores to their surfaces, and how they evolve over billions of years. By understanding the complex interplay between rotation, convection, and magnetism in our own star, we gain insights that apply to the countless billions of other stars throughout the universe. The simple fact that the Sun rotates differentially rather than as a solid body reveals fundamental truths about the nature of stars and the physics of plasmas in extreme conditions. Chapter 2. Lunar phases are not caused by Earth's shadow. If you have ever heard someone explain why the moon changes shape throughout the month, you might have been told that Earth's shadow falls on the moon, blocking sunlight and creating the phases we observe. This explanation seems logical at first glance. We know that the moon does not produce its own light, but instead reflects sunlight. We know that Earth is larger than the moon and positioned between the Sun and moon at least some of the time. It makes intuitive sense that Earth might cast a shadow on the moon, just as a person standing in sunlight casts a shadow on the ground. This explanation is completely wrong. The phases of the moon have nothing to do with Earth's shadow. Instead, they result from our changing perspective as we view the moon from Earth, while both bodies orbit through space. The moon orbits Earth once every 29.5 days, and during this orbit, the Sun illuminates the moon from different angles relative to our viewpoint. Sometimes we see the fully illuminated side, sometimes we see the dark side, and sometimes we see portions of each, creating the familiar cycle of phases. Think about it this way: the sun always illuminates half of the moon, just as it always illuminates half of Earth. The moon is a sphere, and at any given moment, one hemisphere faces the sun and receives sunlight while the opposite hemisphere faces away and remains in darkness. This is true regardless of where the moon is in its orbit around Earth. The phases occur because our view of this illuminated hemisphere changes as the moon moves around us. When the moon is on the opposite side of Earth from the sun, we see the entire illuminated hemisphere, creating a full moon. When the moon is between Earth and the sun, the illuminated hemisphere faces away from us, and we see the dark hemisphere, creating a new moon. The intermediate phases happen when the moon is at various points along its orbit. During a waxing crescent, which occurs just after new moon, we see a small sliver of the illuminated hemisphere. The word waxing means growing, so a waxing crescent is a crescent that will grow larger over the following nights. During first quarter, approximately 1 week after new moon, we see exactly half of the illuminated hemisphere. The term quarter refers not to the amount of the moon we see, but to the moon having completed 1/4 of its orbit around Earth. During waxing gibbous, we see more than half but less than the full hemisphere. The word gibbous comes from a Latin term meaning hump or bulge, describing the swollen appearance of the moon when it is more than half illuminated but not yet full. Then comes full moon, when the entire visible face is illuminated. After full moon, the cycle reverses through waning gibbous, where the illuminated portion shrinks from fully lit to half lit. Waning means decreasing or diminishing. Third quarter shows half illumination again, and waning crescent shows a shrinking sliver before the cycle returns to new moon. You can prove this to yourself with a simple observation. Look at the moon during its crescent phase, either shortly after new moon or shortly before. Notice that the illuminated part is a smooth curve, part of the moon's circular edge. Now consider Earth's shape. Earth is a sphere, which means any shadow it casts should be circular. But during a crescent moon, the boundary between light and dark on the lunar surface, called the terminator, forms a curve that is part of an ellipse, not a circle. If Earth's shadow were causing the phase, the boundary would always be circular because Earth is round. The fact that crescents and gibbous moons show elliptical boundaries proves that Earth's shadow is not involved. Another way to prove that phases are not caused by Earth's shadow is to observe when they occur. A crescent moon is often visible during the daytime, hanging in the blue sky alongside the sun. In fact, during a waxing crescent, the moon rises in the morning and sets in the evening, spending much of the day visible in broad daylight. How could Earth's shadow be falling on the moon when the sun and moon are both visible in the sky at the same time? Earth's shadow always points away from the sun, extending into the darkness of space on the night side of our planet. When the moon is visible during the day, it is not in Earth's shadow and cannot possibly be eclipsed by it. So when does Earth's shadow actually fall on the moon? Only during a lunar eclipse. A lunar eclipse occurs when the sun, Earth and moon align in a straight line with Earth in the middle. During this alignment, Earth's shadow does fall on the moon, and we can watch the shadow creep across the lunar surface. The shadow has two parts: the umbra, which is the dark central region where sunlight is completely blocked, and the penumbra, which is the lighter outer region where sunlight is only partially blocked. As the moon passes through the penumbra, it dims slightly. As it enters the umbra, the darkening becomes dramatic, and the moon may turn a deep reddish colour. The red colour during a lunar eclipse occurs because Earth's atmosphere bends some sunlight into the shadow. blue light is scattered away by atmospheric particles, the same process that makes our sky blue during the day. But red light, with its longer wavelength, passes through the atmosphere more easily and bends around the edges of Earth, illuminating the moon with a copper or blood red glow. The exact color depends on atmospheric conditions at the time of the eclipse. If there has been a recent volcanic eruption that put large amounts of dust into the stratosphere, the eclipse may be darker because more light is blocked. Lunar eclipses are relatively rare, occurring only a few times per year at most. If lunar phases were caused by Earth's shadow, we would see an eclipse every single month during the full moon, but we do not. The reason is that the moon's orbit around Earth is tilted about 5 degrees relative to Earth's orbit around the Sun. This tilt means that most of the time when we have a full moon, the moon passes either above or below Earth's shadow rather than through it. Only when a full moon occurs while the moon is crossing the plane of Earth's orbit, at points called nodes, does the alignment become precise enough for an eclipse to occur. The misconception that Earth's shadow causes lunar phases is surprisingly persistent. Even well-educated adults sometimes hold this belief, often because they were taught it incorrectly as children and never questioned it. The misconception may be reinforced by diagrams that attempt to show lunar phases, but accidentally make it look like Earth is casting a shadow. Educational illustrations sometimes show Earth in the center with the moon at various positions around it, and shadow effects in the drawing can suggest that Earth is blocking light when that is not the actual mechanism being illustrated. The misconception may also be reinforced by the term eclipse, which some people mistakenly think is just another word for the moon's phases, rather than a distinct and rare phenomenon. The word eclipse comes from Greek and means abandonment or failing, referring to the sun or moon failing to provide its usual light. Ancient cultures often had mythological explanations for eclipses, frequently involving celestial monsters or demons devouring the sun or moon. Some cultures made loud noises or shot arrows into the sky during eclipses to frighten away the monster and save the celestial body from being consumed. Understanding the true cause of lunar phases helps explain many other astronomical observations. It clarifies why the moon rises and sets at different times throughout the month. During new moon, the moon is near the sun in the sky and rises at sunrise and sets at sunset, making it invisible against the bright daytime sky. During first quarter, the moon rises around noon and sets around midnight, spending half the day and half the night visible. During full moon, the moon rises at sunset and sets at sunrise, remaining visible all night long. During third quarter, the moon rises around midnight and sets around noon, visible primarily in the morning sky. The phases also explain why we sometimes see the moon during the day and sometimes only at night. Many people are surprised to see the moon in the daytime sky and think something unusual is happening, but daytime moon visibility is perfectly normal and occurs during specific phases. The waxing crescent and first quarter are visible in the afternoon and evening sky. The waxing gibbous and full moon become visible in the late afternoon and evening. The waning gibbous and third quarter are visible in the late night and morning hours. Only during the new moon phase is the moon essentially invisible because it is too close to the sun's position in the sky. Understanding lunar phases also helps explain why the illuminated portion of the moon always points toward the sun. If you look at a crescent moon and imagine a line perpendicular to the illuminated edge, that line will point approximately toward the sun's position in the sky. This makes perfect sense when you realize that the sun is illuminating the moon, and the terminator, the boundary between light and dark, is where the sun's light is hitting the spherical moon at a glancing angle. The same principle applies to any spherical object illuminated by a distant light source. The phases of the moon have been observed and recorded for thousands of years by cultures around the world. Ancient astronomers tracked the lunar cycle with impressive accuracy, using it as the basis for calendars and for predicting eclipses. The Babylonians developed sophisticated mathematical models of lunar motion that could predict the moon's position in the sky and its phase many years into the future. The ancient Chinese also kept detailed records of lunar phases and eclipses, compiling centuries of observations that modern scholars still study today. Many ancient calendars were lunisolar, meaning they tried to reconcile the cycle of lunar phases with the cycle of seasons caused by Earth's orbit around the Sun. This is challenging because 12 lunar cycles of 29.5 days total only 354 days, 11 days short of a solar year. Various cultures developed different solutions to this problem, including occasionally adding an extra month to keep the calendar aligned with the seasons. The Jewish and Islamic calendars are still lunar-based, though they handle the discrepancy differently. Today, we have a complete mathematical model of the moon's orbit and can predict phases and eclipses with perfect accuracy centuries into the future. We understand not only the basic geometry of the Sun-Earth-Moon system, but also subtle perturbations caused by the gravitational influence of other planets, variations in Earth's rotation rate, and the gradual spiraling outward of the Moon as tidal forces transfer angular momentum from Earth to the lunar orbit. This deep understanding allows us to calculate precisely when eclipses occurred in ancient history, helping historians date historical events recorded in ancient texts that mention eclipses. Chapter 3. The Moon does rotate on its axis. Here is another common misconception about the Moon that surprises many people when they first encounter the truth. The Moon always shows the same face to Earth, a phenomenon you can verify yourself by observing that the familiar pattern of dark and light regions on the lunar surface never changes. You always see the same features in the same positions, month after month, year after year. The Sea of Tranquility, where Apollo 11 landed, is always in the same location. The large crater Tycho, with its distinctive bright rays, is always in the southern hemisphere. This consistency leads many people to conclude that the Moon does not rotate at all, that it is locked in place with one side perpetually facing Earth and the other side forever hidden from our view. This conclusion is incorrect. The Moon does rotate on its axis, completing one full rotation every 27.3 days. This is exactly the same amount of time it takes the Moon to complete one orbit around Earth. Because these two periods match perfectly, the Moon keeps the same face pointed toward Earth throughout its orbit, a condition called synchronous rotation or tidal locking. Far from being an unusual or unlikely coincidence, this synchronous rotation is the natural end state for any moon orbiting close to its planet over geological timescales. To understand why the Moon must be rotating, imagine walking in a circle around a lamppost while keeping your face pointed at the post at all times. As you complete your circuit, you have turned your body through a full 360 degrees relative to the surrounding environment, even though you maintain the same orientation relative to the lamppost. You have rotated on your own axis once during your single orbit. The Moon does exactly the same thing, rotating once per orbit to keep the same face pointed toward Earth. If the Moon did not rotate at all, we would see all sides of it over the course of a month. Picture a ball with a painted dot on one side. If you carry that ball in a circle around your head while keeping the dot pointed in a fixed direction toward a distant wall, the dot will face you when the ball is between you and the wall, face away from you when the ball is on the opposite side of your orbit, and face sideways during the intermediate positions. You would see all sides of the ball during one complete orbit. The fact that we do not see all sides of the moon proves that it must be rotating at the same rate that it orbits. The synchronous rotation of the moon is not a coincidence, but the result of tidal forces acting over billions of years. When the moon first formed, it probably rotated much faster than it does today, completing a rotation in just a few hours. Current theories suggest the moon formed from debris blasted into orbit around Earth by a massive collision between the young Earth and a Mars-sized object called Theia. This debris would have been rotating rapidly as it coalesced into the moon, giving the newly formed satellite a rapid spin. But the moon's gravity creates tidal bulges on Earth, raising the level of the oceans on the side facing the moon and on the opposite side. Similarly, Earth's gravity created tidal bulges on the moon, deforming its shape slightly. In the early solar system, when the moon was still molten or partially molten from the heat of its formation, these bulges were much more pronounced. The moon's interior was soft and pliable, allowing Earth's gravity to raise substantial tidal bulges in the molten rock. As the moon rotated, the tidal bulges tried to remain aligned with Earth, while the moon's rotation tried to carry them forward. This created enormous friction and released energy in the form of heat. The molten interior of the moon was being continuously kneaded and flexed by tidal forces, like squeezing a stress ball over and over again. This process, called tidal heating, generated tremendous amounts of thermal energy. This energy had to come from somewhere, and it came from the moon's rotational energy. The moon was literally slowing down its rotation to power the tidal heating of its interior. Over millions of years, the moon's rotation gradually slowed down as rotational energy was converted into heat and dissipated into space. Eventually, the rotation rate slowed enough that the tidal bulges remained fixed relative to Earth, always pointing toward our planet. At this point, no more energy needed to be dissipated, and the moon's rotation rate stabilized. The moon had become tidally locked, with one hemisphere permanently facing Earth and the other permanently facing away. The mathematical description of tidal locking involves the concept of tidal torque. When a rotating body has tidal bulges that are not perfectly aligned with the direction toward the body creating the tides, there is a gravitational torque that acts to slow or speed the rotation. For the moon, Earth's gravity pulls more strongly on the near side bulge than on the far side bulge because the near side is closer. This creates a torque that opposes the moon's rotation if the moon is spinning faster than it orbits. The torque continues until the rotation rate equals the orbital rate, at which point the bulges remain stationary and the torque vanishes. This process of tidal locking is extremely common in the solar system. Most large moons are tidally locked to their planets, including Jupiter's 4 large Galilean moons, Saturn's major moons, and many others. Io, Europa, Ganymede, and Callisto all keep the same faces pointed toward Jupiter. Titan, Saturn's largest moon, is tidally locked to Saturn. Even some binary asteroid systems show tidal locking, with both objects keeping the same faces pointed toward each other. The dwarf planet Pluto and its moon Charon are mutually tidally locked, meaning each keeps the same face pointed toward the other. An observer on one side of Pluto would always see Charon in the same position in the sky, while an observer on the opposite side of Pluto would never see Charon at all. The process operates on any pair of bodies where tidal forces are strong enough and where enough time has passed for dissipation to slow the rotation. The closer a moon orbits to its planet, and the longer the system has existed, the more likely tidal locking becomes. The strength of tidal forces decreases rapidly with distance, following an inverse cube law. Double the distance, and tidal forces decrease by a factor of 8. This means that distant moons experience much weaker tidal forces and take much longer to become tidally locked, if they ever do. The far side of the Moon, sometimes incorrectly called the dark side, remains hidden from Earth, but is not permanently dark. It receives just as much sunlight as the near side over the course of a lunar month. During a new moon, when the near side is dark, the far side is fully illuminated by the sun. During a full moon, when the near side is bright, the far side is dark. The term dark side is misleading and should be replaced with far side to avoid confusion. The phrase dark side probably became popular because of Pink Floyd's famous album, The Dark Side of the Moon, but the usage predates that album and has been common in science fiction for decades. We can only see the far side of the Moon using spacecraft that orbit the Moon or travel beyond it to capture images of the hidden hemisphere. The first images of the Moon's far side were captured by the Soviet Luna 3 spacecraft in October of 1959, revealing a landscape quite different from the familiar near side. The far side has far fewer dark maria, the smooth plains of solidified lava that create the pattern we recognize as the man in the moon. Instead, the far side is heavily cratered and dominated by lighter-colored highland terrain. This difference in appearance may be related to the tidal locking itself. The asymmetric gravitational environment created by Earth's proximity could have affected how the Moon's interior cooled and how volcanic activity distributed itself across the surface. The near side experienced stronger gravitational interactions with Earth, which may have kept the crust thinner and allowed more volcanic lava to reach the surface, filling low-lying impact basins and creating the smooth dark maria. The far side had a thicker crust that resisted volcanic flooding, leaving the ancient cratered landscape largely intact. Interestingly, tidal locking is a two-way process. Just as Earth's gravity has slowed the Moon's rotation and locked it tidally, the Moon's gravity is slowing Earth's rotation and gradually locking us to the Moon. The Moon raises tidal bulges in Earth's oceans, and as Earth rotates, these bulges are carried forward by Earth's rotation. The Moon's gravity pulls back on these bulges, creating a torque that opposes Earth's rotation and gradually slows it down. Earth's rotation is slowing at a rate of about 1.7 milliseconds per century. This means that each century, the day becomes 1.7 milliseconds longer. Over hundreds of millions of years, this effect is substantial. Ancient corals from the Devonian period, about 400 million years ago, show daily and yearly growth rings that reveal there were about 400 days in a year at that time. Since the length of the year has not changed significantly, this means the day was only about 22 hours long back then. As Earth's rotation slows, angular momentum must be conserved in the Earth-Moon system. The angular momentum lost by Earth's rotation is transferred to the Moon's orbital motion, causing the Moon to spiral slowly outward, away from Earth. The Moon is currently receding from Earth at a rate of about 3.8 centimeters per year, roughly the rate at which fingernails grow. Laser ranging experiments, where scientists bounce laser beams off reflectors left on the Moon by Apollo astronauts, have measured this recession with millimeter precision. In the far future, if both Earth and the Moon survive long enough, Earth's rotation will slow down until an Earth day equals a lunar month. At that point, the same side of Earth will always face the Moon, just as the same side of the Moon always faces Earth. This will occur when both the day and the month are about 47 current days long. However, this process will take tens of billions of years, far longer than the Sun will remain a stable main sequence star. Long before mutual tidal locking is achieved, the Sun will evolve into a red giant and likely engulf or destroy both Earth and the Moon. Chapter 4. The Moon does not influence human behavior. Throughout history, people have attributed strange behavior and unusual events to the phases of the Moon. The word lunacy derives from the Latin word for moon, luna, reflecting the ancient belief that the full moon could drive people mad. The term lunatic was used for centuries to describe people with mental illnesses, and the full moon was thought to exacerbate their conditions or trigger episodes of madness. Hospital workers often claim that emergency rooms become busier during full moons. Police officers sometimes report more arrests and disturbances. Teachers and parents insist that children become more hyperactive and difficult to manage when the moon is full. These beliefs are so widespread that many people accept them as established facts, never questioning whether the moon actually has the power to influence human behavior. Scientific research has thoroughly examined these claims and found no evidence to support them. A meta-analysis reviewing 37 different studies that examined relationships between the moon's 4 phases and human behavior revealed no significant correlation whatsoever. The researchers found that of 23 studies claiming to show a connection between the moon and human behavior, nearly half contained at least one statistical error that invalidated their conclusions. When proper statistical methods were applied, the supposed lunar effects disappeared. Other reviews have focused on specific behaviors. A survey of 20 studies examining correlations between moon phases and suicides found that most studies showed no correlation at all. The few that did report positive results were inconsistent with each other, finding different patterns that could not all be correct simultaneously. Some studies claimed suicides increased during full moons, others during new moons, and still others during quarter phases. The lack of consistency strongly suggests that any correlations found were due to chance rather than a real lunar effect. Studies of emergency room visits have been particularly numerous because of the widespread belief among healthcare workers that full moons bring more patients. A survey found that 40% of medical professionals believe that moon phase influences human behavior, despite the lack of scientific evidence. However, when researchers actually analyze emergency room records and compare them to lunar phases, they find no significant correlation. Emergency rooms see roughly the same number of patients during full moons as during other phases, with normal day-to-day variation accounting for any differences observed. A large study by the National Institute of Health examined more than 5,400 patients to find a connection between the lunar cycle and psychiatric emergency room visits. The data revealed only a small and statistically questionable increase in the number of visits to psychiatric emergency rooms when a full moon was present. However, there was a stronger correlation with severe illness and aggressive behaviors at the beginning and end of the moon cycles, not at the full moon. Even this finding has not been replicated consistently in other studies, suggesting it may have been a statistical anomaly or the result of confounding variables not properly controlled for. Another comprehensive study examined records from more than 8,000 psychiatric admissions over a period of 8 years, as well as nearly 2,000 emergency psychiatric evaluations. The researchers found no more admissions on days with a full moon, new moon, any quarter of the moon, a waxing moon, or a waning moon. This held true for psychiatric patients as a whole, as well as for individuals with particular diagnoses such as those with mood disorders or psychotic disorders. The study concluded that lunar phase was not associated in any significant way with psychiatric admissions or emergency presentations. Studies of violent crimes, traffic accidents, and a host of other phenomena have all failed to find any reliable connection to lunar phases. Researchers have looked at homicide rates, assault rates, domestic violence reports, suicide attempts, animal bites, emergency surgery rates, and many other variables, consistently finding no correlation with the lunar cycle. When apparent correlations do appear, they do not replicate in subsequent studies or in different geographic locations, indicating they are likely due to random chance or to specific local factors unrelated to the moon. Why do so many people believe the moon affects behavior despite the lack of evidence? Part of the answer involves confirmation bias and selective memory. When something unusual happens during a full moon, people notice and remember it, reinforcing their belief in lunar effects. The full moon is bright and conspicuous, drawing attention to itself and making people more aware of its presence. When an emergency room is unusually busy during a full moon, staff members notice the correlation and remember it. When the emergency room is equally busy during other phases of the moon, staff are less likely to check the lunar calendar and may not even realize what phase the moon is in. Selective attention creates a false impression that events cluster around the full moon even when they actually occur randomly throughout the month. Psychologists call this phenomenon illusory correlation, the tendency for people to perceive relationships between variables even when no such relationship exists. If someone expects full moons to be associated with strange behavior, they will unconsciously look for and find patterns that confirm this expectation while ignoring or dismissing evidence that contradicts it. This cognitive bias is very powerful and can create the subjective experience of correlation even in completely random data. Another explanation involves availability heuristic. Vivid, memorable events that occur during full moons are more easily recalled than mundane events during other phases. If a particularly dramatic incident happens during a full moon, it becomes associated with that lunar phase in memory. Over time, as similar dramatic events accumulate in memory, all associated with full moons, the person develops a strong subjective sense that full moons cause unusual behavior. The many dramatic events that occurred during other phases are forgotten or not associated with the moon, creating an unbalanced sample of memories that suggests a pattern where none exists. Some people argue that the moon must affect human behavior because it creates tides in the ocean, and humans are mostly water. This reasoning is flawed for several reasons. First, the moon's gravitational pull on an individual human is extremely weak. It is strong enough to raise the ocean's surface by a few meters over distances of thousands of kilometers, but the effect on a human body would be utterly negligible. The gravitational force from the moon on a human is far weaker than the gravitational forces we experience from nearby objects like buildings, cars, or even other people standing nearby. To put this in perspective, a mosquito landing on your arm exerts more gravitational force on your body than the moon does. The gravitational attraction between two objects depends on their masses and the distance between them. The moon is very massive but also very far away, about 380,000 kilometers on average. A mosquito is tiny but in direct contact with your body, and gravitational force increases dramatically as distance decreases. If the moon's weak gravity could affect human behavior, then mosquitoes, furniture, and buildings should have even stronger effects, yet no one claims these things influence our mental state. Second, tides do not occur because the moon pulls water toward it. Tides result from differences in gravitational force across Earth's diameter, creating a tidal bulge on both the side facing the moon and the opposite side. This differential force, called the tidal force, requires vast distances to have any measurable effect. A human body is far too small for differential gravitational forces to create any kind of tide. Even if there were a tiny effect, it would be completely overwhelmed by the much stronger pressure variations we experience from weather systems, changes in altitude, and even standing up or sitting down. Third, the water in the human body is contained within cells and tissues, not sloshing around freely like ocean water. The biological processes that govern human behavior operate at the molecular and cellular level, and are controlled by electrochemical signals, hormones, and neural activity. These processes involve voltage changes measured in millivolts, ion concentrations measured in millimoles, and neurotransmitter releases measured in microseconds. None of these processes are sensitive to the incredibly weak gravitational effects from the Moon. To suggest otherwise requires ignoring everything we know about physics and biology. There is one historical exception that might explain why the belief in lunar effects on behavior persisted for so long. Before the invention of artificial lighting in the 19th century, the full moon would have been the brightest natural light source available at night. People might have slept less during full moons simply because their sleeping areas were brighter, and sleep deprivation could have led to behavioral changes or exacerbated mental illnesses. In an era when most people lived in buildings with poor window coverings and went to bed at sunset, a bright full moon shining through windows could genuinely disrupt sleep patterns. This sleep disruption could have caused real changes in behavior that ancient peoples correctly associated with the full moon, even if they misunderstood the mechanism. In modern times, when most people sleep in darkened rooms with curtains or blinds, and when urban areas experience far more light pollution from streetlights and buildings than from the moon, this effect should have disappeared entirely. The fact that beliefs about lunar influence on behavior persist in modern urban populations, who are largely isolated from natural moonlight, demonstrates that the beliefs are cultural rather than based on actual experience. Studies have occasionally found weak correlations between lunar phases and certain behaviors, but these correlations do not replicate consistently across different studies or different populations. For example, one study found that anxiety attacks were 32% less frequent during the last quarter of the lunar cycle, but this result has not been confirmed by other research and may be a statistical fluke. When hundreds of studies examine dozens of different behaviors, some will show correlations purely by chance, especially if researchers do not properly correct for multiple comparisons. In statistics, this is known as the multiple comparisons problem. If you test for correlations between lunar phase and 100 different behaviors, you would expect about 5 of those tests to show statistically significant results purely by chance, even if the moon has no actual effect on any of the behaviors. Researchers who publish the positive results while filing away the 95 negative results create a biased literature that suggests lunar effects are real when they are actually just statistical noise. The persistence of lunar behavior myths, despite overwhelming scientific evidence, to the contrary demonstrates how difficult it can be to overcome cultural beliefs and anecdotal experiences with data and logic. People tend to trust their personal experiences and observations more than abstract statistics, even when those statistics are based on vastly larger and more carefully controlled data sets. Breaking through this resistance requires not just presenting evidence, but understanding the psychological mechanisms that maintain false beliefs and addressing them directly. Interestingly, some research suggests that merely believing in lunar effects might cause behavioral changes through psychological mechanisms rather than gravitational ones. If people expect to feel differently during a full moon, they may unconsciously alter their behavior or perception in ways that confirm their expectations, a phenomenon called a self-fulfilling prophecy. Emergency room staff who expect busy full moon shifts might be more alert to unusual cases or more likely to remember them, reinforcing their belief even when the actual patient numbers remain unchanged. The moon continues to fascinate us, and that fascination sometimes leads us to attribute powers to it that it does not possess. The moon influences Earth in many real and important ways, controlling ocean tides, stabilizing Earth's axial tilt, and providing light that affects the behavior of many nocturnal animals. but influencing individual human behavior through gravitational forces is not among its effects, despite centuries of cultural belief to the contrary. Chapter 5. Crossing the asteroid belt is not extremely dangerous. If you have watched science fiction movies or television shows that depict spacecraft traveling through the asteroid belt, you have probably seen scenes of pilots desperately maneuvering between tumbling rocks, dodging and weaving to avoid catastrophic collisions. Asteroids fill the screen, so numerous and close together that navigation seems nearly impossible. Ships pass within meters of huge tumbling boulders. Characters grimace with concentration as they thread their vessels through this cosmic obstacle course, barely escaping destruction with each near miss. Laser blasts or photon torpedoes sometimes shatter asteroids, creating cascading debris fields that make passage even more treacherous. These dramatic portrayals have created a widespread belief that the asteroid belt is an incredibly dense and dangerous region of space. The reality could hardly be more different. The asteroid belt is mostly empty space, with asteroids spread across such an enormous volume that spacecraft can pass through it without coming anywhere near an asteroid unless deliberately aimed at one. The average distance between asteroids large enough to be dangerous is approximately 600,000 miles, or roughly 1 million kilometers. To put this in perspective, the distance from Earth to the Moon is about 240,000 miles, or 384,000 kilometers, meaning asteroids in the belt are typically more than twice the Earth-Moon distance apart. The asteroid belt occupies a vast region between the orbits of Mars and Jupiter, extending from about 2 astronomical units from the Sun to about 3.5 astronomical units. 1 astronomical unit equals the distance from Earth to the Sun, roughly 93 million miles or 150 million kilometers. This means the asteroid belt extends from about 186 million miles to about 325 million miles from the Sun, spanning a radial distance of about 140 million miles. But the belt is not a thin ring like Saturn's rings. It is a 3-dimensional torus, a donut-shaped volume with considerable thickness above and below the plane of the ecliptic. Most asteroids orbit within about 10 degrees of the ecliptic plane, but this still represents a vertical thickness of millions of kilometers. The total volume of space occupied by the asteroid belt is approximately 4.7 times 10 to the 25th power cubic miles, an almost inconceivably vast amount of space. The hundreds of thousands of known asteroids are distributed throughout this immense volume, resulting in a density so low that encountering an asteroid by chance would be extraordinarily unlikely. There are approximately 1.1 to 1.9 million asteroids larger than 1 kilometer in diameter in the main asteroid belt, and several million more smaller objects. But even millions of objects become sparse when spread across such enormous volumes. The average density of objects in the asteroid belt is roughly 1 asteroid per tens of millions of cubic kilometers. NASA has sent numerous spacecraft through the asteroid belt on missions to the outer planets and beyond. The Pioneer 10 and 11 spacecraft passed through the belt in the early 1970s on their way to Jupiter and Saturn. The Voyager 1 and 2 spacecraft followed in the late 1970s. Galileo travelled through the belt on its way to Jupiter in the 1990s. Cassini passed through on its way to Saturn. New Horizons traversed the belt on its journey to Pluto. The Juno mission to Jupiter also crossed the belt, as have numerous other missions. None of these spacecraft were designed with collision avoidance systems for asteroids, because engineers correctly understood that the probability of hitting anything was negligible. The spacecraft simply flew straight through the belt without altering course to avoid asteroids, and all of them passed through without incident. Mission planners did not waste fuel on evasive maneuvers or install sensors to detect incoming asteroids because the risk was essentially zero. The spacecraft were far more likely to be damaged by micrometeorites, tiny dust grains that exist throughout the solar system, than by asteroid impacts. In fact, when NASA wanted spacecraft to visit specific asteroids for scientific study, they had to go far out of their way to intercept them. The Dawn mission spent years travelling to reach Vesta and then Ceres, carefully adjusting its orbit multiple times to rendezvous with these targets. The OSIRIS-REx mission took more than 2 years to reach the near-Earth asteroid Bennu, following a complex trajectory that included a flyby of Earth to adjust its path using gravitational assist. If the asteroid belt were as densely packed as movies suggest, reaching these destinations would have been trivial. Simply flying through the belt would guarantee encountering multiple asteroids. But the reality is that asteroids are so spread out that intercepting them requires precise navigation and significant expenditure of fuel. The difficulty of intercepting asteroids actually demonstrates just how empty the asteroid belt is. Imagine trying to hit a specific grain of sand in a volume of space the size of a football stadium. That gives you some sense of the challenge of encountering an asteroid in the belt. The spacecraft must be aimed with extraordinary precision to pass close to an asteroid, typically requiring trajectory corrections along the way as the spacecraft's actual path is measured and compared to the planned approach. If you were actually inside the asteroid belt in a spacecraft, looking out the window, you would most likely not see any asteroids at all with the naked eye. The asteroids are too small and too far away to be visible as anything more than faint points of light, indistinguishable from background stars without a telescope. Even Ceres, the largest object in the asteroid belt with a diameter of about 950 kilometers, would appear as nothing more than a dim star-like point from most locations in the belt. Smaller asteroids would be completely invisible without optical magnification. Even though there are hundreds of thousands of asteroids large enough to be catalogued and millions of smaller ones, the vast majority of the sky in any direction would be completely empty. You would see stars, of course, countless billions of them forming the familiar constellations, and the band of the Milky Way across the sky. You would see the Sun, still bright but noticeably smaller than it appears from Earth. You might see Jupiter or Mars or other planets as bright points of light. But you would see no evidence that you were in a special region of space unless you carefully measured your distance from the Sun and compared it to planetary orbits. The misconception about asteroid belt danger likely originated from early science fiction, before much was known about the actual density of asteroids. In the 1930s, 40s and 50s, when asteroid belt stories became common in pulp science fiction magazines, astronomers knew there were thousands of asteroids but had not yet calculated how sparsely they were distributed. Writers needed dramatic scenes of spaceship peril to keep readers engaged, and a field of dangerous rocks made for exciting visuals and tense moments. The image became a standard trope of space opera fiction. Once this image entered popular culture through influential works, it became entrenched and self-perpetuating. Each new generation of science fiction creators inherited the trope without questioning its accuracy, and audiences came to expect asteroid fields to look a certain way based on what they had seen in previous movies and shows. The 1980 film The Empire Strikes Back featured one of the most iconic asteroid field chase scenes in cinema history, cementing the dense asteroids image in popular imagination. Countless other films and television shows have replicated this trope, from Star Trek to various anime series to modern blockbusters. The confusion may also stem from conflating the asteroid belt with other regions of the solar system. Saturn's rings, for example, are genuinely dense collections of countless particles orbiting close together. Navigating through Saturn's ring plane would indeed be incredibly dangerous because the particles are numerous and tightly packed, ranging from tiny dust grains to house-sized boulders, all orbiting at many kilometers per second relative to each other. A spacecraft attempting to pass through the rings would be sandblasted by countless impacts. Chapter 6. Saturn is not the only planet with rings. When you picture the planets of our solar system in your mind, Saturn probably stands out as the one with spectacular rings. Saturn's rings are its most distinctive feature, easily visible through even small telescopes and featured in countless images and illustrations. For many people, Saturn is synonymous with rings, and they assume it is the only planet in our solar system with such a structure. This belief was true for a long time, but modern astronomy has revealed that rings are actually quite common among the planets. Jupiter has a ring system, though it is much fainter and harder to detect than Saturn's. The Jovian rings were discovered in 1979 when the Voyager 1 spacecraft passed through the Jupiter system and captured images showing a thin ring around the planet. Ground-based observations had failed to detect these rings because they are extremely dark and reflect very little sunlight, making them nearly invisible from Earth. The discovery came as a surprise to many astronomers who had not expected Jupiter to have rings at all. The Jupiter ring system consists of 4 main components. The halo ring is a thick inner torus of particles extending from Jupiter's cloud tops outward. The main ring is a relatively bright but very thin structure extending farther out. Beyond the main ring are 2 wide, faint gossamer rings named after the moons Amalthea and Thebe, whose material contributes to these rings. The entire ring system is composed primarily of dust particles rather than larger chunks of ice, which explains why it is so dark and difficult to see. Uranus also has a ring system, discovered in 1977 before the Voyager missions reached the outer planets. The discovery was made using the stellar occultation technique, where astronomers watch a star pass behind a planet and measure how the starlight dims. As Uranus moved in front of a distant star, astronomers noticed that the star's light blinked on and off several times both before and after the planet itself blocked the star. These blinks indicated that narrow rings were passing in front of the star, blocking its light momentarily. The rings of Uranus are strikingly different from Saturn's bright, icy rings. Uranian rings are narrow, dark, and composed of larger particles, more like boulders than dust. The particles range from about 20 centimeters to 20 meters across, making them substantial chunks of material rather than fine debris. The rings are also incredibly thin, only a few kilometers thick in most places. There are 13 known rings of Uranus extending from about 38,000 kilometers to 98,000 kilometers from the planet's center. Unlike Saturn's rings, which contain mostly water ice and reflect 70% or more of the sunlight that hits them, Uranus's rings reflect only a few percent of incident light. They appear to be made of material as dark as charcoal, possibly carbon-rich compounds or radiation-processed ice. This dark composition makes the rings very difficult to observe from Earth, and detailed study required spacecraft observations from Voyager 2 when it flew past Uranus in 1986. Neptune rounds out the quartet of ring-bearing gas giants. Neptune's rings were also discovered using stellar occultation observations, initially detected in 1984, though full confirmation came from Voyager 2 in 1989. Neptune has 5 principal rings, all of them faint and dusty. The rings show unusual structures called arcs, dense concentrations of material that occupy only portions of the ring rather than being uniformly distributed. These arcs are apparently held in place by gravitational resonances with Neptune's moon Galatea. The discovery of rings around Jupiter, Uranus and Neptune challenged the long-held assumption that rings were unique to Saturn. Instead of being an unusual feature, ring systems appear to be common among large planets, particularly gas giants. All 4 giant planets in our solar system have rings, though they vary dramatically in brightness, composition, structure, and extent. This suggests that ring formation may be a natural consequence of having a large planet with moons, as ring material can be generated by impacts on moons, capture of comets or asteroids, or disruption of moons that wander too close to the planet. Even more surprisingly, rings are not limited to planets. Astronomers have discovered ring systems around much smaller bodies, including the dwarf planet Haumea and several asteroids. The asteroid Chariklo, only about 250 kilometers in diameter, has at least 2 narrow rings orbiting it. The asteroid Chiron may also have rings. These discoveries demonstrate that rings can form around objects of various sizes and in different parts of the solar system, making them far more common than anyone expected even a few decades ago. The existence of rings around small bodies raises fascinating questions about how rings form and persist. Traditional theories assumed that rings required a large planet with substantial gravity to hold the ring particles in orbit and prevent them from escaping into space. The discovery of rings around asteroids shows that this assumption was too restrictive. Ring particles can remain in orbit around quite small bodies if the rings are close enough to the central object and if there are mechanisms to replenish lost material. Looking beyond our solar system, astronomers have found evidence of ring systems around exoplanets orbiting other stars. These extrasolar rings appear to be enormous, dwarfing even Saturn's spectacular system. One object called J137b appears to have a ring system 200 times larger than Saturn's rings, with a total diameter exceeding 200 million kilometers. If Saturn had rings this large, they would be easily visible from Earth with the naked eye, appearing larger than the full moon in our sky. Chapter 7. Uranus has dark rings and Neptune has thin rings. This section expands on the previous discussion but dives deeper into the specific characteristics that make the ring systems of Uranus and Neptune so different from those of Saturn and even from each other. While most people learn that Saturn has rings, few appreciate how unusual and distinctive the ring systems of the other gas giants are. Understanding these differences reveals important information about how rings form, evolve, and interact with their host planets. The rings of Uranus are among the darkest objects in the entire solar system. They reflect only about 2% of the sunlight that strikes them, making them appear almost black. This is in stark contrast to Saturn's rings, which are composed largely of pure water ice and reflect more than 70% of incident light, giving them their brilliant white appearance. The darkness of Uranian rings suggests they are made of very different material, possibly organic compounds, carbon, or heavily radiation-processed ice that has been darkened over billions of years. The extreme darkness of Uranus's rings makes them extraordinarily difficult to observe from Earth. Even with powerful modern telescopes, the rings appear as faint, barely detectable features. Special observing techniques are required to see them at all, including using infrared wavelengths, where the contrast between the rings and the blackness of space is slightly better than invisible light. Observations from the Atacama. Large millimeter array and other advanced facilities have measured the temperature of the rings at around -320 degrees Fahrenheit, consistent with material in the cold outer solar system. The narrowness of Uranian rings is another distinctive feature. While Saturn has broad continuous rings extending over hundreds of thousands of kilometers, most of Uranus's rings are narrow ribbons only a few kilometers wide. The Epsilon ring, the brightest and most massive of Uranian rings, varies in width from 20 to 96 kilometers as it circles the planet. This variation in width is unusual and suggests that the ring is not in a simple circular orbit, but instead follows a slightly elliptical path, causing it to be compressed in some locations and expanded in others. The narrowness of these rings poses a theoretical challenge. In the absence of confining forces, narrow rings should spread out over time as particles collide and exchange momentum. Computer simulations show that rings as narrow as those around Uranus should dissipate within tens of millions of years at most. The fact that they still exist billions of years after Uranus formed suggests that something is actively confining them and preventing them from spreading. The most likely explanation involves shepherd moons, small satellites whose gravitational influence herds ring particles and keeps them confined to narrow paths. The rings of Neptune present their own unique characteristics. Neptune has 6 known rings, all of them tenuous and dusty. Unlike the particle-rich rings of Saturn or the boulder-filled rings of Uranus, Neptune's rings consist primarily of fine dust, with particles measuring microns to millimeters rather than centimeters to meters. This dusty composition makes the rings extremely faint and difficult to detect, requiring sensitive instruments and careful observation techniques. The most unusual feature of Neptune's rings is the presence of ring arcs, concentrated clumps of material that exist in only portions of the rings rather than being uniformly distributed. The Adam's ring, Neptune's outermost ring, contains 5 distinct arcs that have been given names: Fraternité, Égalité, Liberté, and Courage. These arcs contain significantly more material than the surrounding ring and appear brighter in images. The arcs are apparently stable over at least several decades, as they were detected in ground-based observations in the 1980s, and were still present when Voyager 2 imaged them in 1989, and when the Hubble Space Telescope and ground-based telescopes observed them in subsequent decades. The existence of stable ring arcs is theoretically problematic. Orbital mechanics predicts that concentrated clumps of material in a ring should spread out over time due to differential orbital velocities. Material in the inner parts of an arc orbits slightly faster than material in the outer parts, causing the arc to smear around the entire ring in a matter of years or decades. The fact that Neptune's arcs have persisted for at least several decades without spreading suggests they are being actively maintained by some mechanism. The leading explanation for the stability of Neptune's ring arcs involves orbital resonances with the moon Galatea. Galatea orbits just inside the Adam's ring, and particles in certain parts of the ring are in a 42 to 43 resonance with the moon. This means that particles complete 42 orbits for every 43 orbits completed by Galatea. At this precise resonance, the gravitational influence of Galatea can bunch particles together and prevent them from spreading, creating, and maintaining the observed arcs. Observations from the James Webb Space Telescope and other modern instruments continue to reveal new details about the ring systems of Uranus and Neptune. These observations show variations in brightness and composition that were not visible in earlier images. They reveal how the rings interact with the planet's magnetic fields and with charged particles trapped in the magnetospheres. They provide information about the size distribution of ring particles and how this distribution varies between different rings and different parts of the same ring. The discovery and characterization of rings around Uranus and Neptune required decades of patient observation using multiple techniques. The initial discoveries came from stellar occultations, where astronomers measured the dimming of starlight as rings passed in front of distant stars. Spacecraft flybys provided dramatic confirmation and detailed imaging. Ground-based telescopes, equipped with modern detectors and adaptive optics, have continued to monitor the rings, tracking how they change over time and discovering new structures not visible in earlier observations. Understanding why Uranus and Neptune have such different ring systems from Saturn and from each other remains an active area of research. The differences may reflect different formation mechanisms, with some rings being ancient features dating back to planetary formation and others being young structures created by recent collisions between moons or capture of comets. The differences may also reflect different levels of ongoing activity, with some rings being actively replenished by material from moons or meteoroid impacts, while others are slowly dissipating and will eventually disappear. The ring systems of the outer planets demonstrate that our solar system is far more complex and varied than simple textbook descriptions suggest. Each planet has its own unique characteristics shaped by its formation history, the properties of its moons, the structure of its magnetic field, and countless collisions and interactions that have occurred over billions of years. Studying these differences teaches us about the processes that shape planetary systems and helps us interpret observations of ring systems around exoplanets orbiting distant stars. Throughout this examination of 7 solar system misconceptions, a common theme emerges. Many things we thought we knew about our cosmic neighborhood turn out to be incomplete, oversimplified, or simply wrong. The Sun rotates but differently at different latitudes. Moon phases result from changing perspectives, not Earth's shadow. The Moon rotates synchronously with its orbit. Lunar effects on human behavior are psychological, not gravitational. The asteroid belt is mostly empty space. All 4 giant planets have rings, not just Saturn. Uranus and Neptune have distinctive ring systems unlike anything around Saturn. These corrections are not mere technicalities, but fundamental revisions to our understanding of how the solar system works. They demonstrate the power of scientific observation and the importance of questioning assumptions. They show how technology, from improved telescopes to spacecraft exploring the outer planets, can overturn long-held beliefs and replace them with more accurate knowledge. They remind us that science is not a static collection of facts, but a dynamic process of discovery, correction, and refinement. Perhaps the most important lesson from these misconceptions is humility. If we can be so thoroughly wrong about objects we have observed for thousands of years, objects relatively close to us in cosmic terms, how much more might we be wrong about distant galaxies, the nature of dark matter, or the ultimate fate of the universe? The history of astronomy is largely a history of discovering that the universe is stranger, more complex, and more wonderful than we imagined. There is every reason to believe this process will continue, with future generations looking back at our current understanding and finding it quaint or incomplete.